All right, we're recording. Tina, what do you?
See, his goal is die hard. I feel like this is a note for people about this class. I knew it. Yes.
So this is gonna be okay. So we have one student I've never met before. So what's your story?
My name is Diego. I'm from Brazil.
Okay.
My major in Brazil is network computers. I am a student in the ESL class, and I take the class here for. I think that's really good for my English and my knowledge. It's basically.
Okay. And you've had computer programming, and have you had computer programming before?
Yes, in Brazil I see something about development programming, but my specialty is network, not programming.
Okay.
I will do my best.
Well, it could be hard, but you'll probably do better than Dane. That's Dane back there, by the way.
Just add don't talk about Sweden ever.
Oh, you guys are in for a rude awakening.
No.
So,
What? It's all ski.
nope.
I'll cry.
No, even better. All right, so let's talk. Okay, so this is 450 system software. This is me. You guys know me. I've had most of these guys like 20 times in class. So feel free to joke around. This is Tina. A lot of them have nicknames. So
That's not one of those.
that's a birth name. He was hockey's not in this class.
He's probably done with his minor. Oh, is he?
All right, so here's my email address. There's my cell phone number. Text me if you need me. Call me. I won't answer. Best way to get a hold of me is either text or email. This is when this class meets. We're going to teach this. What?
Do we need the book? No.
Well, hold on. Which book? This one? No, you don't need this one. You need the Dragon book.
What?
Computer science classes.
This is a famous book. It is. It's just like the dinosaur book. This is the Dragon Compiler's book. See how it has a dragon on the front of it? It's another famous.
Can I borrow that PDF version?
Yeah, so you should all order this online. I will not give you a copy of this.
Cubic.
Yeah, so this is that book from that Dr. Locklear gets. I'm not going to use it. But you should all have it. Excellent book. Blah, blah, blah. So, at the end of this class, you'll learn that all computer programming languages are created equal. Computer programming is not computer science, rather is the tool that we use to solve problems in an applied way, much like a hammer is to a carpenter. That computer programming can be fun, and so can writing a compiler. Appreciate the effect of a Christian worldview on the discipline of computer science and gain an understanding of the responsibilities and ethical issues a Christian professional will face in the computerized society. Check. All right. Grades for the class. Homework, 45% of the class. 15% pop quizzes. Well, all my quizzes will be pop quizzes. 20% midterm, 20% final. Normal grading scale. Questions, comments, concerns, bribes. You guys are going to want to start thinking about bribes here pretty quick.
Weekly bacon, what'll that get us?
So, let's talk about last semester a little bit. So remember how in 470, the programming language theory class, you guys kept complaining, says, oh, we hate Scheme. I really wish this was in a language we know like Java, blah, blah, blah. You will be begging that we would go back to using Scheme in this class.
I would be impressed.
Last semester, we focused on writing an interpreter for a programming language called Simon, right? Using Scheme and an intermediate language known as Beaker. That's Beaker. And that's Simon. So, anyways, tell me. Remember back in one of your first programming classes with me, we probably had a slide saying there are two kinds of programming languages, interpreted and compiled languages. Remember that?
Yeah.
All right, so let me come over here to my slides. So two kinds of programming languages. Oh, hold on, I have two kinds of programming languages. We have interpreted and we have compiled. What is the difference between an interpreted language and a compiled language?
Is this a surprise?
Oh, this was from Carrie. Yeah, this time I have bacon. Last time she had her folks buying me alcohol. She knows how to bribe a professor. Totally a true story, too. Is anybody going to answer my question?
Do you have a question, sir?
Interpreted languages versus compiled languages. What's the difference?
The compiled language is like in machine code, so it can run natively. You need an interpreter program to interpret an interpreted language.
Huh?
In real time.
All right, so interpreted languages, we should think immediately that there might be a performance hit, right? Because there's an interpreter involved. Okay, so for instance, our friend here is from Brazil, right? So your language Portuguese, right?
Yes.
Okay. I don't speak Portuguese. I speak bad English and even worse Spanish. I can barely order a Taco Bell. Okay? So if he were talking to me in Portuguese, I would need an interpreter, somebody who understood Portuguese and also understood English in order to take whatever you're saying, convert it into English so I can understand it. And if that's happening in real time, there's going to be a time drain there, right? I'm going to have to wait for that interpreter to get to actually make the translation. Now, so interpreted languages do that interpretation during runtime, which leads to slower performance. Compiled languages do their interpretation, if you will, prior to runtime, at compile time. Okay? So hopefully at runtime we don't have the performance hit. So the idea would be he would write me a letter in Portuguese. I would give it to my interpreter who would then spend their time rewriting it in English, hand me the letter in English when it was time for me to read it. Okay? So there was no time lost in the middle. Well, time was spent, but not from my perspective. I was delivered a letter in English. Make sense? Specifically, what does a compiler do? If you had to give a concise definition of a compiler, what would you say? Oh, I love bacon. It's my favorite vegetable. What did you say your first name is again?
Diego.
Diego?
Yes, like Spanish. Diego.
Like that
Yeah.
kid on the TV, the cartoon guy.
Yeah.
You got Dora, and you got Diego, right?
Yeah, I remember
All right, well, you can answer my question? Compile? What's a compiler? Concise definition of a compiler.
Wait. Okay, good. So I was gonna say that it breaks down like something like a code graph into machine code, so it's got a one-to-one relationship with the things the processor can do, some crap like that.
Okay, so you said some decent things there, but then you inserted wrong facts into places where there should have been right facts.
Well said.
So a compiler, actually, is there such thing as a wrong fact? Or is that an oxymoron?
That might be an oxymoron.
Okay, so anyways, a compiler translates a high-level language into a low-level language. Okay? I guess officially a compiler translates one language into another language. But we've always thought of it as a high-level language like Java, C#, Objective-C, whatever, into a low-level language like assembly. Okay? So a high-level language being a language that has a one-to-many relationship to the CPU. So our CPU, let's review. Hold on. We need to do this, I think, for Dane. What is man, I'm getting bacon grease all over my keyboard.
First world problem.
All right. So, what's a CPU?
Central processing unit.
Okay, that's what it stands for. You always say
Always fall for it.
processing unit. That's in the Bible, isn't it?
No.
How do you spell it?
EUNICH.
E-U-N-I-C-H, like that?
Yes. That's it. Tally.
Okay, central processing unit. Okay, that's what it stands for. What is a CPU? If you had to give me a concise definition of what a CPU does, what would you say?
Computes. Crunches number.
Okay. How does it accomplish that?
Logical operation.
Follows a set of instructions.
Addition. Multiplication.
Okay, follows a set of instructions. So the CPU has I usually refer to them as magic tricks. CPU has a big collection of magic tricks that it knows how to do. And what the people at Intel who've made our CPUs, what they've done is they've decided a generalistic collection of problems can be solved with this set of magic tricks. Just like a human being, we have hands and our fingers and we can move them all sorts of different ways. And when we solve a problem, we solve them in terms of, I'm going to reach out, I'm going to pick up the hat, so I'm going to put my arm there, squeeze, lift up. I'm using the different tools that I have in a certain order to solve a problem. CPUs are the same way. They have a bunch of magic tricks that they know how to do, and if you use them in a certain order on the right kind of data, you come up with a solution. So, CPU is a collection of magic tricks. All right. Now, compiler translates from high-level language to low-level language. High-level has a many-to-one relationship with the CPU. Low-level has a one-to-one relationship with the CPU. Okay, so that means that every line of code we write in a high-level language like Java translates into many, many, many magic tricks that the CPU knows how to do. Many to one. Make sense? Actually, it should be one to many, right? I think it's relatively interchangeable, but I think this is probably more correct. All right. Now, a low-level language like assembly, that's us writing each instruction, and each instruction we write translates into exactly one magic trick the CPU knows how to do. Okay? Now, in the big scheme of things, yeah, so Diego, last semester, they took a programming language theory class with me, and we used a programming language called Scheme in there. Dane did not like that language. The rest of the class loved it.
Love very loosely. Thanks for that, Paul.
Whoa, you're changing the rules.
Huh? Yeah.
2 a second ago, man.
Yeah, don't you remember that slide set from like back when you were in 200 or 250?
Recreating things from
There's like...
There's 5.
Threes, twos, and 2 threes.
Alright.
It is what we're talking about. Spent hours in a room full of whiteboards. Nothing the same seven.
That's not pretty terrible.
All right, so there are 3 kinds of programming languages. We have machine language, we have low-level languages, we have high-level language. Machine language is a zeros and ones, right? So we have the little 2-digit keyboard, 2-button keyboard. Just sit out there and just program it out.
And you're done with your name.
Not quite. Okay, low-level language, we just explained, has the one-to-one relationship. So every line of code we write in a low-level language translates into one magic trick the CPU knows how to do. A high-level language, every line of code we write translates into many instructions that the CPU knows how to do, many magic tricks. Okay? Now, human beings definitely don't want to program in zeros and ones, right? That's not in our feature set. We would make mistakes very, very quickly. Low-level language we can almost tolerate, but only for a second. Okay? We don't want to have to write programs. Now, you know, Carrie, breakfast places also serve coffee. Terrible.
It's just terrible.
I've had 4 pots of coffee so far today. I'm just mowing through it.
Decaf,
You meant
right?
cups.
Yeah.
right?
All decaf, actually. It didn't have even 1 cup of regular.
Are you like not seeing?
You're gonna have a situation
Go to the
like
back to make sure it
I've been. I can't.
be held from the
Skype section.
All right. So low-level language, one-to-one relationship. Human beings could tolerate this, but it's not our preference. We like power tools, right? Okay. High-level languages like Java, they allow us to accomplish much more with a lot less. That's the kind of thing that we like. All right. So our preference would be to write our code in high-level languages, then utilize a tool to get it down to a low-level language that the computer can actually understand. And that's where a compiler comes in. So compiler translates from a high-level language, what we like to program in, and converts it into a low-level language, something that has a one-to-one relationship with the CPU. All right, that makes sense? All right, so. Oh, I need to. So, let's jump over to our book here. It's like it's one of those things where like revenge is a dish best served cold. You guys are going to be praying for Scheme so shortly. It's going to be awesome. Huh? Last semester, you guys kept complaining about, oh, Scheme, if only we could do this in Java. Well, now you get your wish.
This would be revenge if we had killed you. There's no revenge. You're just like torturing us twice.
I'm enjoying it.
You thought you knew
This is
pain.
just the first revenge.
All right, so name of the book is Compilers, Principles, Techniques, and Tools. Make sure you get the 2nd edition. All right,
yeah, second position.
here's your ISBN number. Oh, and Diego, I record all my lectures and upload them to YouTube, so there'll be a link so you can rewatch them. It's a good way to put yourself to sleep at night.
Remember, use ad blockers.
Yeah.
Yeah, you got to turn off your ad blockers and click on every ad. Yeah, I made $1.25 last semester.
Wow. Welcome.
All right,
Where's my
Stop
cup?
paying you the normal professor salary. You're making bank off.
making bank.
Yeah. That's mad, yo.
Making more.
Yeah. Calculated huge like my salary.
Okay, so I'm just going to kind of skim through the first couple pages here. It basically shows exactly what we just talked about. So what does a compiler do? Takes your source program, compiles it into a target program. High-level language, probably, into a low-level language, probably. All right. Somewhere in here they show a Java as example language. Like Java is kind of a hybrid, where we have our Java program, runs through a translator, which converts it into Java bytecode, an intermediate language. Okay? Kind of like Microsoft intermediate language, missile code for .NET. So here's our intermediate program, which runs on a virtual machine, and then we have our output. So the virtual machine is a computer built in software. This is an interpreter. This is a compiler, right? Source program to some other program. This is the active compilation. This is an interpreter. Okay. So we already kind of covered this. What are the difference between a compiler and an interpreter? What about advantages? What's the advantages of a compiler over an interpreter and vice versa?
Compiler's faster at runtime.
Okay, at runtime. Important note there.
Interpreters can be on many different platforms as long as you have the translator on those different platforms. So it's easier just to port between.
You could have a compiler on many different platforms too.
But if you're going to compile like a language, it's going to like be native to that. Because when you need like a different compiling program, then or rewrite it.
Well, I think you're really talking about virtual machines.
Yeah.
So you're saying compiler is fast at runtime. What's the downside of a compiler?
Your program is super giant. It can take a long time to compile. You might not want to compile the whole thing.
Okay. So compilers are complex programs, right? Now, let's put that on hold there for a second. Interpreters. What's the advantage of an interpreter?
It only interprets the code you're using.
Well, here, let's go. What's the disadvantage of an interpreter? That's the easy one.
Slow.
Slow at runtime, right? What's the advantage of an interpreter?
You can run it anywhere where that interpreter exists. So
It's kind of the same crap Paul was.
yeah, but I don't know what Paul was talking.
Well, that's, his name's Coleslaw, by the way. It's not Paul, it's Coleslaw.
It's also a verb.
So what's the advantage? The disadvantage of an interpreter is that they're slow at runtime. What's the advantage of an interpreter? So advantage of a compiler is that it's fast at runtime. Disadvantage of an interpreter is that it's slow at runtime. What's the advantage of an interpreter?
I guess depending on the task and things like scripting or things where you're going to be doing stuff on the fly, you just don't want to spend the time to compile it.
Okay, I could see that where, you know, there's that step of compilation, it's 2 steps instead of 1. Okay, I could see that. From a computer user perspective, we don't necessarily care because we usually just hit play, right? And the magic happens behind the scenes. So what's the advantage of an interpreter?
Sometimes you want program really slow. That's all theoretical.
Slow is all relative because our computers are so fast today that even a slow program might seem to be just as fast as a fast program. Would you agree that interpreters are significantly more simple to create than a compiler?
I don't think the end user knows that.
No, but we do. So remember that class last semester when we wrote an interpreter and you guys bitched about it?
Oh no, I know what's going to happen. I don't remember that.
Well, we're writing a compiler in this class. What are the advantages of an interpreter is that they're easy to write. The disadvantage of a compiler is it's highly, highly complex.
Last trigger on this.
Very difficult to write a compiler. Very difficult to write a compiler well.
I'm not going to worry about that.
Going back here, can you give me an example of when human beings would write code in a low-level language today?
Legacy stuff.
Like if you're embedding code in C or C++ to speed up like a block point.
Okay. Much better answer than I expected, actually. Can you give me a specific example of when that might happen?
Like if you have maybe like a nested for loop or something. No, that would
Well, here, let's go this route. So let's say you're writing a video game, and you're writing it in C++, and you compile it. The compiler is going to take your C++ high-level code and convert it into low-level assembly language, right? Okay. Now, that low-level code is what actually executes when the game is running. Now, for video games, speed is very, very, very important. There might be a certain aspect of your game that is running slower than it could run because of what low-level code the compiler created. you might be able to go in as a human being and write a more streamlined block of low-level code. Because the compiler is writing what it believes is efficient, foolproof code where you can go in and say, well, I know this particular error will never happen here. My compiler didn't know that, but I know that. So you can get rid of a bunch of maybe error checking in there and just write the streamlined low-level code for that one part of the game, something like that. So that's where a human being might still want to write something in a low-level language. Okay, so compilers, fast at runtime, highly complex to write. Interpreters, slow at runtime, very easy to write. Okay, so last semester's class, easy. This semester's class, impossible. Is
That seems like an accurate.
what I want you to come out of that with. I'm out of bacon.
Oh no. These bunkers.
That's what this is.
Okay, so this is what happens. This is called a language processing system. We have our source program. It goes through a preprocessor. Then we have a modified source program. So this preprocessor kind of prepares your source code for being compiled efficiently. Then we compile it. We get our target assembly program, which is our low-level code. Then it goes to the assembler. What's an assembler? Assembler is a interpreter which takes assembly language code and translates it into, I don't want to say machine code because it doesn't translate into zeros and ones. It does. It translates it into the lookup table for those magic tricks on the CPU. So it takes your instructions in assembly language and converts it to the equivalent magic trick for the CPU. That's what the assembler does. So in many ways, it's an interpreter. But it's not happening at runtime, it's happening at compile time. So you could actually argue that it is a compiler. The assembler is a compiler, that it converts from one language to another language. It just happens to be low level to low level. Okay? So then you have relocatable machine code. That is a set of instructions that set of ordered magic tricks that the CPU on this particular computer knows how to handle. So it's relocatable as long as you take it to a machine that has the same architecture. So when you buy a video game or something like that, and it says minimum system requirements, Pentium 3, 450 megahertz, or whatever it says is the minimum system requirements, it means that this program was compiled against that architecture. And any processors that are newer than that are backwards compatible with that. So it should still work. But any processors that are older with that aren't necessarily guaranteed to work because this code might reference a magic trick that didn't exist in an older architecture, but does exist on that architecture and all newer ones. That makes sense? All right, so we have our machine code, then our linker loader. These are library files. So there are a bunch of things that already exist on your system that weren't part of the code that you wrote, but get wrapped into the code that you wrote when you talk about taking it and moving it from machine to machine as part of an installer or something like that. Okay. The structure of a compiler. So, this is so exciting. This is going to be impossible. All right, so we're going to write our compiler in several different steps, and we will write it in Java, seeing as though that's what you guys are most comfortable with, right? And the good thing is the book also uses Java as their example language. So we start off by reading our source program in as a stream of characters, one character at a time, building up tokens, where a token is like a word or something like that. Okay? Then we send it into the first part of our compiler. So think of this entire thing, all these different steps here, as being inside of one giant box that we call a compiler. And it's kind of like going through this filter. So the first thing is our lexical analyzer. That just sounds scary. Does that remind you of anything, this word right here from last semester? Let's reference last semester. Huh? Lexical address. What did lexical address do? Last semester we wrote that scheme code that took a lambda expression and pumped out the same lambda expression with lexical addresses replacing all identifiers. What did it mean for there to be a lexical address? What was a lexical address? Remember, we have all sorts of scary sounding words. Just the word lexical immediately makes it 10 times scarier than it actually is. It means something stupid.
Depth and position.
Depth and position of where this variable is, right? In the environment. What does a lexical analyzer do? It creates, well here, we have a better example, I think, a little farther down. Something like this. So let's say this is our input code right here. Position is equal to initial plus rate times 60. That's just a line of high-level Java code or something, whatever it is, okay? What it's going to do is this first step, this lexical analysis, is going to rewrite that line to look like this. We have an identifier at position 1. This is a symbol, followed by an identifier at position 2. This is where it's found in our environment for lookup. This is a lookup table. Okay? So we're going to look up identifier at index 2 inside of our identifier table, and we put it inside the identifier table as we found it, reading it in one character at a time. That make sense? So as we read in these tokens, we found the first token, boom, we said, this guy is an identifier. What do we do with identifiers? Well, we put it into our list of identifiers at a specific bucket, in this case bucket 1, and then the lexical analysis rewrites this position to be identifier at bucket 1. Make sense? Then we have our symbol, which is the equal sign, our next identifier, symbol which is the plus sign, our next identifier, symbol that is the multiplication sign, then symbol that is ultimately will be a hard-coded integer, but we're going to find out that integers don't make sense and everything's done with floats. Not important right now, but so the idea is that lexical analysis is the process of going through your program and rewriting it to be simpler for the next step of the compiler. That make sense? So, first phase of a compiler is called lexical analysis, or scanning. I haven't heard scanning in a long time for calling, because scanning sounds too, like, safe.
Too friendly.
It's too friendly, that's it.
Everybody would be making compilers.
Right, there's just scanning. Second you're calling it lexical analysis, like, okay, I'm not doing that. Okay. The lexical analyzer reads the stream of characters making up the source program and groups the characters into meaningful sequences called lexems. For each lexem, the lexical analyzer produces an output as output a token of the form token name, this is a type, and the attribute value, which in our case so far what we've seen is a position. Then it passes to the subsequent phase, the syntax analysis, which puts it into like a tree structure. We'll see that. Oh my gosh, this is just going to be a nightmare. So exciting. So exciting. Doesn't this? How many of you are excited about this? Doesn't this seem cool?
I'm excited because I'm
Almost done with what? School? What are you going to do afterwards? You mean done with school for the day, or like for life, or kind of both?
No, there's always in school. Maybe computers.
You've lost me. All right, so in the token, the first component, token name, is an abstract symbol that is used during syntax analysis, and the second component, attribute value, points to an entry in the symbol table for this token. Okay? Information from the symbol table entry is needed for semantic analysis and code generation. Oh, so exciting. Just more terrifying phrases. I just love these. All right, so we saw this example already. Position is a lexeme that would be mapped into a token, ID1, where ID is an abstract symbol standing for some identifier. And we were used to identifiers from last semester, right? And 1 points to the symbol table entry for position. All right. Symbol table entry for an identifier holds information about the identifier such as its name and type. So the idea here is that as we do this lexical analysis, every single time we run into, from our perspective, a variable name, that's kind of what they're dealing with here initially, they're saying, we see a variable name, we need to store that somewhere. So we're going to put the variable name into this symbol table, and with that variable name, we're probably also going to put the type of that variable. So this goes down to how do we handle strongly typed languages. And if you remember correctly, there's 2 types of programming languages, right? This is just so fun. There are 2 types of programming languages. Strongly typed, loosely typed. What's a loosely typed language? Okay, it's a language that does not require us to define the type for a variable at the time of defining a variable. So we can store an integer in a variable 1 second and put a string in that same variable another second. Okay, what does it cost us to have a loosely typed language? What's the overhead? Let's ask it that way.
It has to figure out what type it is.
At runtime, we need something, usually it's called a type inference engine. Another scary phrase, right? Type inference engine. Okay. So we need a dude at runtime that whenever we want to use what is inside of a variable, it checks to see what kind of value is, it tries to infer what kind of value is actually currently in that variable. That takes time, okay? Which means our programs slow down. Typically, loosely typed languages are also interpreted languages. Make sense? Because those are languages that already don't have a focus on speed. They have a focus on elegance and, I guess more times than not, being noob programmer friendly. So like most, like VB is a good example. Visual Basic is probably the epitome of programming language for beginner programmers. So like if you write in other languages and you tend to make a zillion mistakes, go and write VB code because you'll still make the mistakes, but it won't complain. If you try to take an integer and typecast it to an ice cream cone, it works. It really does. Yeah, it's amazing. So loosely typed languages are dumb languages. That's actually not always the case, but to be honest, I don't see a great argument for loosely typed languages to even exist. Anybody have one? Go ahead. No, I know they do exist. No, I'm just saying they're all wrong.
Well, I guess, again, like just if you're looking, maybe like for scripting, if you want on-the-spot scripting, it would be faster, I guess. Lazier, but faster.
Well, I mean, that's the problem. It's marginally faster, but it's definitely lazier. And doesn't that introduce a I don't know, just bad programming practice?
Maybe if that's like the only language somebody does, but if they like for programs are obviously gonna compile and use that way. They do that with a strongly typed language, and then for just, so if they want to do real fast, use, a loosely typed.
Okay, so you pretty much agree with me that loosely typed languages are languages for idiots.
For the peasants.
It's a peasant language. That's right. Go ahead.
So you're saying that forcing the programmer to keep track and make sure they're putting the right things in the right variables is more lazy than just doing type things and having the compiler yell at you for you.
Well, say this again.
So
So in a loosely typed language,
you have to keep track because the mistakes are like on you. You have to know the semantics of
Yep.
what you want. But in a strongly typed language, you can be lazy and just be like, "Oh, the compiler told me I did that wrong," and like go fix it. You don't have to keep track of anything.
no, I mean it's not a horrible. I mean that's not a horrible argument, but it really becomes a catch-22. And on one hand, okay, even if I agree with you, you're still as a programmer who's choosing to go the extra mile to keep track of what is in their variables. You're still producing a slower language, a slower executable. So why should that exist? Why would we, if we make the assumption that we're putting an additional burden on the programmer and getting a worse, inferior result, right? Go ahead.
I guess it's the right tool for the right job, though. Like, well, because I mean, like, they think Java or C#, they're a lot easier than C++, but they're for the most part, since they run, the processors are so fast now, it really doesn't make that much of a difference, except if it's like an operating system.
You know what the real punchline is?
It depends.
No. See, Matt here is arguing that it's the programmer either being lazy or not being lazy. The reality is it's the person who wrote the language. Loosely typed languages are far easier to write than strongly typed languages. Now, interpreters for loosely typed languages are more difficult to write from the type inference engine perspective. Yeah.
I was just gonna say, because that keeps bringing up the ability to like script something being faster than making a whole new build, like changing AI or something like that. But you could still have like a interpreted language that was strongly typed and then get the best of both worlds in that situation, I guess.
Yeah, an interpreted language, a strongly typed language does not have to be compiled. They just tend to be compiled. Yeah.
I'd say, I guess, like in languages where you do a lot of operator overloading, that would be a case where it make more sense to have the strongly typed. But I guess in Python, because it's my experience, the operator overloading is as important. There's not as much of an emphasis on having that.
PHP can do that too.
So maybe the argument is that loosely typed languages, being interpreted languages, tend to lend themselves to be able to make quick changes to the program with instantaneous results rather than having to recompile and re-upload the binary. So there very well might be some advantage to that, especially in web technologies.
Yeah, I guess if you're loosely typed, it is a lot easier to probably change like method declaration.
Yeah, because you just do that from your phone and throw it back up there, and because you don't have to compile it. Okay, well, I disagree. So anyways, there are two types of programming languages, strongly typed and loosely typed languages. So in this case, compiled languages are typically strongly typed languages. So not only are we keeping track of the identifier name in our symbol table, we're also keeping track of other pieces of information like its type. And maybe even additional information if we have to start thinking about different levels of environments and things like that. That make sense? So that's the symbol table entry for an identifier holds information about the identifier such as its name and type. The assignment symbol, equal sign, is a lexem that is mapped into the token equal sign. Since this token needs no attribute value, we have omitted the second component. That means we don't need to look it up in our symbol table. Therefore, we don't give it an index in our symbol table because this is reserved in the language, right? This is a reserved symbol. Don't put equal signs in your variable names and stuff like that. Actually, I think you could have variable names in equal signs in your variable names. You just can't have a variable named equal sign. Since the token, blah, blah, blah. We could have used abstract symbols such as a sign for the token, but for notational convenience, we have chosen to use the lexeme itself as the name of the abstract symbol. So in this case, they would have treated this guy as kind of his own special thing called the assign operator, if you will. But now this simple compiler that we're talking about here, well, just the first step of the simple compiler, lexical analysis, we're treating everything as a symbol. Just some symbols we need to keep track of, other symbols are just things we know about that are built into the language. Make sense? Okay. Initial is a lexeme that is mapped into the token ID2. So just another identifier at bucket 2 in our symbol table, where 2 points to the symbol table entry for initial. Plus is a lexeme that is mapped to the token blah. Rate is a lexeme that is mapped to ID3. Star is a lexeme that is mapped to blah. 60 is a lexeme that is mapped into the token 60. We're still treating it as an identifier, but we're not putting it into the symbol table because there is nothing to actually look up. 60 is something that's built into the language, but it is going to need some additional interpretation later on. Okay? Blanks separating lexemes would be discarded by the lexical analyzer. And we've seen this before. I always harp when I teach your first couple of programming language classes about how important it is to indent and things like that. By now, you guys all have your own style. You know, some of you put the curly braces right underneath the starting point and then another one right below that. I think, Joey, you put yours at the end, right? You have your starting curly brace at the end of a function and then your closing one left justified underneath the name of the function. I think I've seen you write that way.
I actually switch a lot.
Really?
So.
Okay. Well, in any case, I teach it one way, but the most important thing is that you have some sort of structure to your program. But that's for human eyes. The reality is the compiler doesn't care. You could put your entire program on one gigantic line. Okay? And it's just going to read it in as a character string and put it through the lexical analyzer. And at the end, it's ignored all your spaces and carriage returns anyways. Okay? So the interpreter, the indenting and stuff like that is for human eyes, and you should continue to do that. I'm just saying it's for humans, not for the interpreter, or not for the compiler in this case. Okay. So, at the end of the day, lexical analysis will produce that for us from this portion of the, for this one line of code. We read this guy in and ultimately produced this. Make sense? Okay. I want to talk about your first assignment, which I think is due Friday. So let me pause here. We'll talk about this tree representation next time. So on Angel, first of all, there is a thing here I'm doing new this semester called Homework Directions and Self-Assessment Template. If you click on this, it tells you about your different assignments and things like that. It tells you how you can turn stuff in, what format you can turn it in. All right. Also, every single time you submit an assignment, whether it's a paper or a program, I want you to self-grade yourself. This is going to give me the opportunity to know where I can give you partial credit and where I can't. All right. So every single time you submit an assignment, I want you to copy these last 4 questions, paste it into the box where you're submitting your assignment, and answer them. So first one. Yeah, always make that smaller. No, I'm serious. Important.
Okay.
All right. All right. So this is your opportunity to tell me which parts of the assignment you struggled with and why you struggled with it and how you tried to get past struggling with it. Because more often than not, what I'm getting nothing submitted. And when you submit nothing, you may have spent 10 hours and turned in nothing, or you may have spent 1 hour and turned in nothing, or you, maybe like Dane, spent no hours and turned in nothing. Okay. So I want some commentary about the effort that was put into this so that I can take that into, could you lie to me in this? Sure. But it's probably going to end up showing up at some point, okay? So do this for you and me for every one of your assignments, okay? If you don't provide this for me, I'm just going to give you 0. So even for this first assignment, it's important. Lessons. Okay, so under homework, first assignment's right here. This is due Friday. Write a 2 to 3 page paper which answers the following questions. What is a compiler? Well, we already talked about that. Why do we need them? Then pick a popular C or C++ language compiler. Only compilers for those languages. Some examples would be GCC, G++, CC, CC, C++, CPP. Those are some examples. Okay, so pick a popular C or C++ language compiler and summarize its features and why one would pick that compiler over another compiler. So now we want to start thinking about how are compilers compared. Since we're going to be writing them, how are we going to make sure our compiler is the best one that's ever existed?
By hiring someone else.
All right, make sense? And that paper is due on Friday by midnight, but we'll be back on Wednesday and we'll start talking about the tree representation.
3 more assignments.
What is class?
Huh?
Our last semester, is that